Okay. Yeah, so today we'll discuss convergence of random variable. So just a quick recap. Um, so we have four modes of convergence, right? So convergence in probability and almost sure convergence, and convergence in mean, and then convergence in distribution. Right, so convergence in probability implies xn's are sequence of random variables, and x is a random variable that it is converging to. So convergence in probability means that um, that given any epsilon, any epsilon, that they two differ by more than epsilon tends to zero in probability. Okay, the probability tends to zero. Okay, not the difference tends to zero. Okay, that is one thing. And yeah, so convergence in almost sure sense is okay. So almost sure convergence is for every sample point omega, the sequence xn of omega should converge to x of omega, right? And the set of points where they converge, if you take the probability, that should be one. So only then you say that it is converging almost surely, right? So I've just elaborated a bit, and uh, the other way to state that is the xn of omega not going to x of omega is zero. That means every point on which the probability is assigned that should converge, right? So just take, I mean, see, for fixed omega, this xn gives you a sequence. So what it means for a sequence to um, converge is not to converge. Okay. Uh, so there exists some epsilon, right? And for that epsilon, for every n, right, there exists a member of that sequence an that satisfies this for n greater than n. This is just by flipping the definition of the convergence of sequence. Okay, so just translating this to symbols, like there exists means the union, and for every goes to intersection, right? The same thing I've translated it to set form, right? And this is it. So here 1 by r is playing the role of epsilon, right? And just translating this to the random variables, right? The same thing. So this set, right, differing by more than xn of omega, x of omega differing by more than epsilon should go to zero, right? So since this should hold for every r, we just omit this r, and it is equivalent to writing this. Okay, so this is what this inner thing. If you call an as an event, right, that xn and x differ by more than epsilon is nothing but a lin sup of an, if you remember from the initial classes, uh, right? So this is it. This is the characterization of almost sure convergence. Okay. Um, so just to have a recap, I just written down this. And what does it mean to convergence in mean, right? Arc means especially, right? This is expectation that difference of x and x for r, this should go to zero. The value of this thing, right? E of this thing should go to zero as intent string. Okay. And it is easy to see that convergence in mean implies convergence in probability, right? And what is the fourth mode of convergence? Is convergence in distribution. right? So each xn is a random variable with the distribution fn, right? Xn tends to x in f, means that fn of x should go to f of x for all x wherever f is continuous. Okay, so that's it. Let's see the problems. Okay. Now, xn's are sequence of IID random variables taking values between 0 and 0.5. If e of xn square tends to 0, then xn converges in probability, right? So, yeah, so e of xn square tends to 0. You can write this in this way and can say that it converges in rth main. Here r is 2, converges to 0, right? So this is coming from Markov inequality. This is given to you, and this is coming from Markov inequality, right? Probability xn greater than epsilon is less than or equal to e of xn square by epsilon square, right? And what else? And just take the limits here, right? So this is given, right? This one is going to 0, and that's why it is converging in probability, right? So any questions on this? Okay, so xn is a sequence of ID random variables same in 0 to 0.5, and if all xn's have a mean e of xn is 0.2, right? And variance is going to 0 as n approaches to infinity, right? For every n, and they are IID. Then does it converge in probability? If it converges, where it is converging? You just simply apply the same thing, Chebyshev inequality here, or Markov, it's the same thing. Um, right? So you get this and take the limits on both sides, right? Because it is given variance is going to 0, it goes to 0, and x converges to ex 0.2. That's it. That's the second question. And the second part to this is, now Zn is the product of x1 to xn, right? Where does Zn converges to? Right? Um, so it is easy to see that at any point omega, right, your x1 is taking values from 0 to 0.5 only, right? And um, all the values are less than 1, right? And assume the worst case that is taking 0.5, right? As n tends to infinity 0.5 per n, right, it goes to 0. Basically, it converges in probability, to be specific. In converge, it does almost surely convergence. Um, so yeah, I just written down informally, right? So mod Zn greater than epsilon, right? Since Zn is positive anyways, you can remove that. So one way to attain this is this thing, right? Because they are all less than 1, the product should to be greater than epsilon, then each of x1 should be more than epsilon. It's not the only way, just one way to see this. Right? So each of this is again less than 1, right? And they will be same because it is IID, and then again you can see it is tends goes to 1. We can consider the worst case actually. If all xn's takes the highest possible value, which is 0.5 with probability 1. I mean, this is not possible because mean is given to be 0.2, right? It will be, what should I say? Uh, Yeah, it is not exactly 1, right? It will be just less than 1 because your mean is given to be 1, right? Again, right, the probability Zn greater than epsilon is uh, some value less than 1 raised to n, right? That goes to 0. That is need not be 0.5 exactly, it is something less than 1. And another way to argue this is because it converges almost surely, it does converge in probability, right? Yeah, so let's go to third question. Here we are given this xi's IID random variables with mean 0 and variance 2. Yj's are again IID random variables with mean 2. There's no information on variance here. Xi and Yj are independent for all I and j. So sigma xn square over n, where does it converge in probability? Right, so this is classical result of weak law of large numbers, and right, so you just need to compute because xi's are id, even xi squares are also id. So this, as in the limit n tends to infinity, it converges to e of x square. E of x square in this case is 2. So by weak law, it converges to 2 in probability. The same thing holds for zi, xi, yi, right? And e of zi is this thing. Xi, y are independent. Xi is 0 mean, then it is 0. Again, in probability, it converges to 0 by weak law. Okay. Any questions on this? Okay. Um, okay. So we have defined sample space omega of p as this, right? Omega is your 0 to 1, and f is the set of all the possible Borel subsets in restricted to 0, 1. So basically all possible open intervals. And f is the uniform distribution, the probability measure on this random variable, right? That is specified by this p. And now we have a random variable, sequence of random variables with uniform distribution defined like this: 1 by 2 minus n to 1 by 2 plus n. Okay, so where does it converge to? So just to see, just plot it x1, right? This is the density and this is the distribution, right? Minus 1 by 2 to 3 by 2, right? So the distribution is ramp from minus 1 by 2 to 3 by 2. Again, when x2 goes from 0 to 1, 0 to 1, again a ramp. So this is classic uniform distribution. Again, put n is equal to 3, get 1 by 6 to 5 by 6, right? It's again ramps, right? And x4, 1 by 4 to 3 by 4, right? This again ramps. So as you see, it keeps increasing the ramp, right? And the width in the density keeps shrinking, right? In the limit, what happens is you are converging to a singleton set. So constant width, now constant 1 by 2, right? All the random variables are converging to 1 by 2. And its distribution is step at 1 by 2. That's it. Clear or anything here? Okay. So we have another problem. So one person puts 1 rupee coins in a piggy bank. Okay, and the number of coins that are added on a day is like a tossing a die, right? So takes 1 to 6 with probability 1 or 6. Find the approximate probability that it takes at least 80 days to collect 300 rupees, right? So this phrase of, taking at least 80 days to collect 300 rupees. So in 80 days, it should collect at most 300 rupees, right? So these two phrases are equivalent. Okay, this and this thing. So if xi denotes the number of coins that is put into piggy bank, right? So we need the probability that this thing happens, right? Event of this. Here n is 80. And because it is 1 to 6, taking 1 over 6 probability, 1 over 6 probability, mean is 3.5 and variance is 35 by 12. Right, so same thing, just do subtraction of n times mu both sides. N is 80 here, right? And divided by sigma times root n, right? Sigma is square is 35 by 12, so sigma is square root 35 by 12 times. And so coming, you see where we are going here is towards the central limit theorem, right? If Sns are a sequence of random variables, then xi is a sequence of random variables, and S denotes the sum. Then S minus n times mu divided by sigma root n converges to standard normal. Okay, so that's it. So this is the standard normal distribution. So z is less than or equal to some constant, right? Just evaluate this, it will turn out to be 1.309. So phi denotes the distribution function of standard normal, right? So any questions on this? Yeah, you can just do an experiment on this. You will end up with the same thing, but I don't know what is the value of this 1.3 here. So 1.3 is, I mean, I don't know, it's like 1.5 sigma. Um, so yeah, another interesting question is, I think I merged a different set of PDFs. Okay, no problem. So this is the question. N balls are distributed to n boxes. And if n sub n denotes the number of empty boxes, right? Capital N sub n denotes the number of empty boxes. And we want to know what is the probability that the box is empty. I mean, asymptotically. So n divided by n, as a n is small n is the total number of balls, and capital N sub n is the number of empty boxes, right? The total number of boxes small n. So fraction of boxes that are empty as n tends to infinity. Okay, so if we denote say I1 to In as the box being empty, ith box being empty, right? So first box empty, second box empty, and all nth box empty. So what is the probability that say I1 first box is always empty, right? So that is the probability that you fill the balls in the boxes 2 to n, right? So there are n minus 1 boxes, and the desired probability is n minus 1 whole power n by n power n. Is this clear? Why is this n minus 1 per n divided by n per n? Okay, so we want the probability that first box is empty. That means you are distributing the balls from 2 to n. So basically, first ball can go to any one of the n minus 1 boxes. Second ball can go to any one of the n minus 1 boxes, right? So that is n minus 1 per n. N minus 1 stands for number of boxes, and the numerator is the number of balls. And that you are dividing by total number of possibilities, n per n. Okay, why is the power of n, right? So first of all, okay, so how should I put it? So in how many ways first ball can be given to box number 2 to box number n? N minus 1, that's true. Again, in how many ways you can give second ball to these n minus 1 boxes? Yeah. Box can have more than one ball. Right. So what is for second ball? First ball it is n minus 1. Second ball is also you can put it in n minus 1 ways. Right. So nth ball is also in n minus 1 ways. So in total you have n minus 1 raised per n. Okay. So this is same for I, any I, so, and I mean I1, I2, IN, right? There's nothing special about first box here, right? This thing. So that's why if you take En, expectation of n is n times p, because E of I2 and E of IN, they are all same, right? And okay, so basically we wanted to compute the variance of Nn, right? Um, so to compute variance, I mean, you will see why do we want variance. What is the second moment of this thing, E of n square, right? You just sum up these things, right? If you expand this, what you'll get is E of I1 square plus I2 square plus so on IN square, right? I1 square plus I2 square plus IN square is same as I1 plus I2 plus so on IN, because they take 0 or 1, right? So the first term is the same as expectation of I1 plus I2 plus so on IN, right? That we have denoted by n sub n. Just written directly E of n sub n. And the second term is E of I sub I and I sub j, right? The total you have exhausted n terms here, and remaining are n into n minus 1 terms here. Okay. So we want to evaluate this, right? What does it mean? When does this random variable take one value of 1? If I sub I is 1 and I sub j is 1, that means two boxes are empty, right? So again, when two boxes are empty, total number of possibilities are n minus 2 per n divided by n per n. And because you have this thing, right, summing over n into n minus 1 terms, and you get this, right? I should have written a sigma here, but yeah. Right, so just the variance is second moment minus first moment square, right? You know what is E of n sub n square, right? It is E of n plus this thing, this the whole term, right? This whole term minus E of n whole square, that is same as this thing, right? Now what do we need is this n sub n divided by n, right? So where does it converge in probability, right? This fraction, right? You just define this as some random variable yn and as n sub n divided by n, and we want variance of y, right? That is nothing but variance of n divided by n square, right? So that you'll get something like this, okay? And this will in the limit it will go to 0, because this term will go to 0 and this will go to e power minus 2. This will also go to e power minus 2 in the limit. And because variance is going to 0, right? Now apply the Markov inequality on yn, right? Markov-Archbishop, right? So yeah, so where does E of yn go? Again, before that is same thing, E of n by n, that is n minus 1 by n per n, right? So we are dividing by n, that's why this n goes down from E of n, right? This n. That's it. So in the limit n tends to infinity, this goes to e power minus 1. And you want to see where does it go in probability, right? So yn minus e by n, right, by Chebyshev inequality, right? In the limit, variance goes to 0 of yn. That's why yn goes to mean in probability, which is 1 over e. So any questions here? Yeah, this is a bit complex, but yeah. Is it clear? Yeah. And yeah, so before going to there, we just, okay, we'll come back to this later. Yeah, so this is a problem where you want to find an example where the sequence of random variables converges in probability but doesn't converge almost surely. Okay. So yeah, so let X be a uniform distributed random variable, and x1 of s is s. This s is random. Small s is random, again drawn uniformly between 0 and 1. Okay, and I of s. I of s is 1 if s is between 0 and 1. Okay, so x2 of s, I am defining it by s plus I of 0 to 1 by 2 of s. I of 0 to 1 by 2 of s is 1 if s is between 0 and 1 by 2. And same thing goes for I of 3, but the support is 1 by 2 to 1. Similarly, x4 of s is s plus I of s 0 to 1, 1 by 3. x5 goes from 1 by 3 to 2 by 3 and so on. Okay. So I'm not sure if my general term is correct here. It's n of n plus 1 by 2. I just written it. Right. So okay, so this suffix may not be correct, but so some function of n, let us say, that is going from x greater than epsilon is what? This is 1 over n, right? 1 over 3, basically. Epsilon here, you can take it to be, say, um, how much? So I of s takes 1 if s is in this interval. That's a closed interval, right? That is defined in terms of n. So 0 to 1 for x1, x2 it is for x2 and x3 it is like 0 to 1 by 2. Again x3 it is 1 by 2, 1 by 2 to 1. x4, now you make for x4 you make 3 parts. Not for x4 you make x4 to x6, let's say you make 3 parts, 0 to 1 by 3, 1 by 3 to 2 by 3, and 2 by 3 to 1. Right now x4 is s plus this I of s, and between 0 and 1 by 3. Right? So now if you see, right, each for any fix any s, okay, that is uniformly drawn from 0 to 1. Now that s, as you vary the n, it can take two values, s or 1 plus s. Now as n goes large, right, the interval where it takes 1 by s, right, that is shrinking, right? So I'm not sure this whatever suffix I have written is correct, but you can find some function of n here and write that as 1 over n. Say x4, the interval length is 1 by 3. Similarly for x5 also it will be 1 by 3, and x6 is 1 by 3. So x7 the interval will be 1 by 4, right? So for any function of n, let's say if you fix um, some function of n and you can get the probability that it is exceeding uh, say 0.5, right? So x of s is what? Here x some suffix of this thing, say it takes value s plus 1, and x is s, right? So that probability of that event happening is the width of this interval, right? And that is going with 1 by n. right? So as n tends to infinity, that probability is 0. This is incorrect actually. Whatever suffix I have written, that is incorrect. But yeah, I hope you got the intuition what I'm trying to convey here. Is that clear? Okay, so that's why it is converging in probability, because that uh, probabilities of that uh, s, like any xn taking value of s plus 1 keeps on decreasing because the widths are shrinking, right? So yeah, that's the reason. Now, does it converge almost surely? For almost surely, what should happen is, for every sample point, sequence should converge, right? So now what you do is fix any s. So draw it from 0 to 1 and fix any s. And now analyze the behavior of x1 to so on xn. Okay, so hypothesis is that it should converge to s. Okay, but you see, fix any s between 0 to 1, right? You can always find that sequence to be oscillating from S and 1 plus S. Okay. You can always find that sequence to be oscillating from S and 1 plus S. I mean, you can give me any number, 10,000 or something, right? That is S. I can find some other number, 100,000 or whatever, which is 1 plus S. So this will never be converging, right? So that's why it doesn't have this almost sure convergence property. Right, so this is a peculiar example of the sequence of RVs where the conversion probability but doesn't converge in almost no sense. Okay, so yeah, so last week I think we left out some questioning confusion, right? Just wanted to cover that regarding the conditional expectation. So we want to know the expected number of tosses to get one head and one tail, right? This was the question. Expected number of tosses to get one head and one tail. So let's assume z as denotes the desired random variable, and we want e of z, right? So what do? Is we condition it on the first toss, and by Tower property of expectation, you just write down, right? And the same thing, e of z, you just expand this outer expectation, right? First toss is head, head probability is 1 by 2. First toss is tail, and tail probability is 1 by 2. That you are expanding this one. Okay. And let's analyze what is this, right? Expected number of tosses given my first toss is it. Again, you can use the Tower property to condition on the second toss as well, right? So this is again second toss is tail. So expected number of tosses given my first is head, second is tail, plus half times expected number of coin tosses given first is head and second is head. Okay. So what is the expected number of tosses? If once you have seen one head and one tail, you are done. Basically, we'll stop the game. Right? That's why it is 2. What is the expected number of tosses when first is head and second is head? Right? This is the same as where you have started with head. Right? So that's why it is 1 plus expected number of coin tosses to get the desired event. Condition on first is head. Right? So substitute back these two in here, right? And you will end up getting expected E of Z given first toss is head as 3. Same thing applies to the first toss is tail. You end up getting 3. and you just average them and you get 3 as a typo. But yeah, that's 3. So any questions?